Okay, so here's another mutual inductance problem. And so you can see it says let V1 of t equal 8 sine 720t volts and let I2 be the clockwise mesh current in the middle loop. Find I2. So, okay, they're saying they want to have I2 right there. So the very first thing I think you need to do is convert everything into the phasor domain and realize that we have these mutual inductor terms that we need to account for. And when we do that, we also should try to bear in mind the standard form that I think we should label everything in when we do that. Okay, so first off, we need to convert the voltage source to the time domain, from the time domain to the phasor domain. And so we have V1 of t is equal to 8 sine 720t. So our omega is equal to 720 radians per second. And we normally have the cosine as our reference, so we need to find what V1 of t is reference to a cosine wave. So sine is cosine of 720t minus 90 degrees. And so when we've got that right there, we can see that our V1 in phasor form is equal to 8 angle minus 90 degrees, which turns out to be, if we go through the magnitude and phase or polar to rectangular form, we're going to get minus 8j, which of course could also be thought of, since this is the complex plane, 90 degrees is down here from the real axis, positive real axis. So we're down that length, we're down that angle, and our magnitude is 8, and so that would give us minus 8j. So that length there is 8, the angle is minus 90 degrees, so we're at minus 8j. Okay, that's not really a big point of this problem, but let's go ahead and put the rest of it in the time domain. So 1 millihenry we needed to convert to the phasor domain from the time domain. So we need j omega L, and that's equal to j. Omega is 720 and L is 0.001. So this is J 0.72. Okay, J 2 millihenries. Well, obviously we can take j omega L, but the only difference is going to be it is twice what we just found, so that's going to be 1.44 J. And of course these units are ohms. And then we've got the two mutual inductance terms that we're going to have, which are 500 nanohenries. So 500 nanohenries. That term is the M term, so we need j omega M is equal to j omega is still 720, M is 500 times 10 to the minus 9, and so when we calculate that, we get J 360 times 10 to the minus 6. And that's in ohms again. Now we've got a capacitor in there, so we've got to get its form, and that's 1 millifarad. So 1 millifarad is going to go to 1 over j omega c, which is minus j over omega c, is going to be minus j over 720 times 1 times 10 to the minus 3. And so this turns out to be 1.39, so minus j 1.39. Okay, so now when we've got everything, I believe, now in the phasor domain, so we can copy this circuit and draw it as if we were in the phasor domain. Okay, so now what we have here is, well, actually maybe I shouldn't have done it this way. Maybe I should just draw it. So we'll have our voltage source, Vs. We have 1.8 ohm resistor. We have a 1 millihenry inductor that we changed to J.72. The dot for the inductor is down there. We have a 1 millifarad capacitor, which was minus J 1.39. Of course, all of these are in ohms here. And we have a 2 millihenry inductor, which we said was J 1.44 ohms. And then we have a 2 ohm resistor there. And finally the dot here is up there, and that mutual inductance term maybe I should say the mutual term is going to be now a J 360 times 10 to the minus 6 ohms, and that's J omega M. Okay, so now everything looks like we're set up to actually do the problem. I2 of t is what we were after, so we'll call this I2 in phasor form. Might as well go ahead and have I1 in phasor form there, I3 in phasor form over here. Now, if I were actually doing this problem very carefully, like I'm trying to do here, I would call the mutual inductance, or maybe I should say the voltages for the inductors according to the mutual inductance form, which has typically the plus at all of the dots, is what we'd like to have for our standard form. So I'll call this one V1, and I'll call this one V2. Now I'm going to call the current, now we're supposed to have the current defined on these as going into the dots on both of them. So typically we need to think of the current going up that way and down that way to be going into the dot. So that's the way we'll reference those in terms of our mesh currents as we write our equations. So our first equation, I'm going to go around the first loop and I'll just say minus Vs plus 1.8 I1. And then remember, most of the time for mesh current method we would want to have just everything in terms of the current. So we'd like to do the inductance and all that stuff in terms of you know, mesh current I1 and I2. So it used to be that I would have just said j omega L times I1 minus I2 and go through it that way. But since we have the mutual term and we've got to make sure we incorporate everything properly, what I would do is just write the voltage and then we'll back substitute the voltage in. So I'll say minus V1 and that's equal to 0. And then for the next one, next loop, I'll have V1 as I'm going clockwise minus J 1.39 times I2 is the only current and it's going clockwise there, and then plus V2 is equal to 0. Okay, again that's leaving V2 there so that I can go back and back substitute what V2 is in terms of the currents. And then finally the last loop, minus V2 plus I3 equals 0. Okay, now that I've done that, typically our mesh equation should only then then have unknown currents. But because we left the voltages across the inductors as voltages, then we've got to write those. And that should be all we have really left at that point. So now we have V1. Okay, what is it? Well, we know it's the j omega L term and the j omega M term. So the j omega L is going to be the J 0.72. The j omega M term is going to be J 360 times 10 to the minus 6. Okay, now the current that we're looking for, the current to satisfy the passive sign convention, the current going into the dot there, and that's why we labeled that voltage V1 from the bottom to the top. That current going into the dot, well, I2 goes into the dot, I1 goes against it, so this should be I2 minus I1. And then the current going, so the mutual term should be the current going into the dot of the other one, and going into the dot of the other one will be I2, going against the dot will be I3, so this is I2 minus I3. And now that we referenced everything, then we can have the net positive out front of all of those. Now we need to do the same thing for V2. Okay, so the V2 term, is going to have the self term, which is J 1.44 times the current satisfying this passive sign convention, which notice that'll be with the dot, or going into the dot, since we defined our voltages being at the dot, or if plus with reference to the dot, minus on the other side, that should be. So I need the current going down through the 1.44 J ohm inductor, and that will be I2 is going down, I3 is going up, so I2 minus I3 is the net current going down, and I need the current going into the dot of the other inductor, so that's going up, and I2 is going up, I1 is going down, so the current that I need is I2 minus I1. Okay, so this looks good, and now I basically have to substitute in I need to substitute in my V1s right here, and my V2s right here and right here. And what I'll have, I also have to substitute in Vs, which Vs is minus 8J. So once I do that, I'll have, basically a 1.8 I1 minus V1. Now that's going to be, once I've substituted, it's going to be in terms of I1, I2, and I3, is equal to Vs, which is going to be minus 8J. And then my second equation will be V1 minus J 1.39 I2 plus V2 equals 0. And then I'll have minus V2 plus 2I3 equals 0. Okay, so that's a little long and drawn out, but notice V1, as I said there, here it's in terms of I1, I2, and I3. V2 we have in terms of I1, I2, and I3. And so right here we also have that. We can get three equations, and three unknowns that we'll have are I1, I2, and I3. And so we should be able to solve for those mesh currents. One of the things that I think you should look at right here for sure, if I were going to approach this right now, I'd probably say, oh, well, V2 is 2I3. So that'll allow me to write 1.8 I1 minus V1 equals minus 8J. The next equation I can write is V1 minus J 1.39 I2 plus V2. Well, V2 I already know is 2I3. That's the easier substitution than substituting this super long expression right there. So that's V1 minus J 1.39 I2 plus V2 equals 0. And now I also have V2 is 2I3, and so V2 being 2I3 basically says 2I3 is equal to I2 minus I3 times J 1.44 plus J 360 times 10 to the minus 6 times I2 minus I1. So now the only other things that I have to back substitute are just the V1 term that I have this big long expression for here, and both of those two spots for V1 right there. So if we solve for me putting this minus V1 in here, I'll have V1, which I can just select here. and then close my bracket off. So that was that 1.8I1 minus V1 equals minus 8J. And then the second equation I can move way over here and replace V1 with that same form. So again, that was the V1, which I'll put in brackets here. And then we had the minus J 1.39I2 plus V2. So let's make sure it's clear there that that is a minus J 1.39I2 plus V2, which was 2I3, equals 0. So now you can see I've got three equations with I1, I2, and I3 as unknowns. So I should be able to solve for I1, I2, and I3. And when you do this, you should get that I2 is 3.126 angle, let's see here, 57.28 degrees. And then I2 in the time domain is that magnitude, 3.126 cosine of omega t, and omega is 720, right? Plus that phase angle, 57.28 degrees. And that's the final solution.